In this example problem, we're going to design a beam to span 70 feet for a building. You can see some of the given properties. We're going to use concrete with an initial release strength of 4 KSI and an ultimate strength of 6 KSI. These will be initial values that we assume, and in the design process, we can always specify a strength that's less or more than that. We're also given our loading. So we have a live load of 60 pounds per square foot and a superimposed dead load of 20 pounds per square foot. We're going to use conventional prestressed steel strands with 270 KSI ultimate strength, and we'll tension them to 0.75 times the ultimate strength. You can see I calculate the concrete modulus at the time of release and at service for us. Our first step is to choose a cross-section type based on our span length and our loading and also the application. There are a number of different design aids that we can use. So there are some for building design, some for bridge design. The one that I'm showing here is from Collins and Mitchell's textbook, Prestressed Concrete Structures. And it's just a way that we can choose an initial shape for building design based on our span length and our superimposed service load. So we have a span length of 70 feet, and we have a superimposed service load of 60 pounds per square foot plus 20 pounds per square foot, which will give us 80 pounds per square foot. So based on this, I'm going to choose this 32-inch deep double T as our starting point. As I mentioned, there are a number of different design aids that we can use. The one shown here is from the PCI Design Handbook in Chapter 3. You can see these are load tables for some of the commonly used precast building products. So this is the double T that we're going to use we're going to try to use for our design. We're going to initially try to not have a topping on it. So it'll be an untopped double T with a 32-inch depth, and you can see we're given our gross section properties for this cross section. So all of our most standardized shapes, you'll be given the gross section properties that you can use in the design process. The PCI Design Handbook also has this table that allows you to get a good idea of the span length and the number of strands and the location of those strands for different loads and different span lengths. So we could come here with our 70 foot span and determine our safe superimposed service load that we need, and then figure out the number of strands that we need and the location of those strands. So for this design, we're going to pretend we don't have this, and we'll use a current point analysis to figure out an initial starting point for strand area and strand location. For our current point analysis, we're going to need a couple things first, and the first thing we'll need to do is figure out our loading. So our self-weight is given based on our section. So for our double T section, you can see that it has a specified self-weight of 591 pounds per foot. Our superimposed dead load and our live loads are given in units of pounds per square foot, and we're going to apply this over the entire top flange of our double T. So the top flange of our double T has an 8-foot width, so we take our pressure load times that 8 feet to get a distributed load that we can apply to our beams. So for our superimposed dead load, we have a load of 160 pounds per foot, and for our live load, we have a distributed load of 480 pounds per foot. We can then find our unfactored moment, our maximum unfactored moment. Again, this is at midspan. So our unfactored moment, or our service moment, is just adding up these distributed loads, so WL squared over 8 to get our midspan moment. And then our factored moment, we're going to include a load factor of 1.2 for our dead load and 1.6 for our live load. and we'll get a factored moment then of 12,264 kip inches. Next, for our current point analysis to figure out our prestressing and the amount of prestressing we need, we'll need some estimated values for E plus KT based on our cross-section shape. So from Collins and Mitchell, we can look at the table that I show here. And for a double T section, we'll use an E plus KT, initial value of 0.7H. So we're going to use this in a design equation that I show on the next slides. In the current point analysis, we're going to estimate the amount of prestressing that we need based on the required prestressing to prevent cracking in our bottom fiber at midspan at service. So yeah, I guess the first thing we need to do is calculate our E plus KT. So we'll have 0.7 times our overall height, 32 inches, which will give us a value here of 22.4 inches. Next, because we're looking at our service condition and our tensile limit, we'll use 7.5 times the square root of our the strength of our concrete at service, 6,000 psi, which will give us a value of 581 psi or 0.581 ksi. Next, we can plug these values into our expression we can derive from our current point analysis to figure out the prestressing that we need. So for us, we have our maximum moment of 754 kip feet times 12 inches per foot minus our section modulus 2,615 inches to the third, and our tensile strength of our concrete, our rupture strength 0.581, and then divide this by our 22.4 inches. So we'll find our prestressing force should be greater than or equal to 336.1 kips. So note that this is a design expression, not an analysis expression, so it's just supposed to give us some kind of basic guidelines about the amount of prestressing that we'll need. So we don't necessarily need to meet this limit to meet any kind of code expressions. So it's just supposed to give us some guidance. So based on this, we can estimate our effective prestressing force, or effective prestressing stress after all of our losses. We're going to just assume 25% losses initially. So then we can calculate our approximate required area is just equal to our 336.1 divided by 152 KSI, which will give us an approximate area here of 2.21 square inches. And we can see that we can try using 16 half-inch diameter strands, which will give us a value that's greater than this 2.21. So yeah, this will be the amount of prestressing that we'll try in our initial design. We're going to assume that we have, or that strand harping is available for this design. Although a straight strand profile should be used if possible, as it makes fabrication of these beams easier. If strand harping is required, then we'll have a maximum eccentricity at midspan and minimum eccentricity at the end of the beams. What we'll do in this current point analysis is we're going to figure out a minimum and a maximum eccentricity, essentially like a range of eccentricities, where if we have the centroid of our prestressing strands in this range, so if we get our prestressing strands in this range here, we'll kind of theoretically meet our stress checks. So what we're gonna do in this design is we're gonna find a max and min at the end, and a max and min at midspan, and then use a single harping point to kind of design our strand. So we'll have a single harping point with a straight strand rather than the parabolic profile I just showed. So one of the first things we'll need to do is, or we can find our eccentricity at the ends of the member. And we can start by finding our maximum eccentricity using the expression shown here. So we can find our KB first. And our KB is just going to be our section modulus for the top, 5,140 inches to the third, divided by our area, 567 inches squared, which will give us a KB here of 9.07 inches. We're going to find our eccentricity, our minimum and maximum allowable eccentricities at the location of our transfer length. So we need to figure out where that is along our beam. Our beam extends to the end of the bearing, and we're going to assume that the center of our support is at the center of our bearing. So this distance from the center of our bearing to the transfer length is going to be the distance that we use when we find our moment. So this distance is our transfer length, which is approximately 25 inches, based on just taking 50 times the diameter of our prestressing strand. And then half of our bearing is 0.5 times 8 inches, which will give us a distance from the center of the bearing to the end of our transfer length as 21 inches. We can then use this distance to figure out our minimum moment, so our moment just from our self-weight at the location of, or at our transfer length. So we can find that to be 423.5 kip inches. Next, we're going to need to figure out our prestressing force after elastic shortening, so at the end of transfer. So this is just going to be our area of our prestressing, which we're starting with 16 half-inch diameter strands, so we have our area there. And then we take this times 187 KSI, which is our assumed stress in our prestressing after elastic shortening, which will give us a value here of 458.2 kips. We can then plug these values all into our expression here for our max eccentricity, and we'll get 9.07 plus our minimum moment 423.5 kip inches plus our section modulus 5,140 inches to the third times our stress limit here 0.379 KSI, and then all this divided by our initial prestressing force 458.2 kips. So we can then find our maximum eccentricity is equal to 14.2 inches. So we can then do the same thing with our minimum eccentricity, using our current point analysis for minimum eccentricity at the end. With this, we can find our top current point, SB, divided by A, so 2,615 inches to the third, divided by our area, 567 square inches, which will give us a KT here of 4.61 inches. We can also find our maximum moment at the transfer length. So the same thing at a distance 21 inches from the center of our bearing. Our max moment is our self-weight plus our superimposed dead load plus our live load, which will give us a moment here of 882 kip inches. We next need to find our prestressing force after all of our losses. So again, we assumed a value for our losses, 25% losses. So we just take our total area, 2.45 square inches times 152 KSI, which will give us a force here after all losses of 372.4 kips. We can then plug all of our values, our tension limits at service, which we're using for this kern points analysis, is 7.5 times the square root of f prime c. So we can see that here. So we can plug all these values into our kern point analysis then, and we'll have our minimum eccentricity equal to m max 882 kip inches minus our section modulus 2,615 inches to the third times our tensile stress limit 0.581 KSI, and then all divided by our final pre-stressing force, 372.4 kips. And we'll get our minimum eccentricity here to be negative 6.3 inches. So this negative number means that it's an eccentricity above the centroid of our section. So we can see then our allowable range here is between negative 6.3, so 6.3 inches above the centroid of our section, and 14.2 inches below the centroid of our section. So these values are just kind of an allowable range, or these aren't set in stone. So we need to lay out our strand pattern to be in between these values, and then we need to end up checking the stresses of our actual design. So again, these aren't firm limits. These are just to give you some guidance during the design process. So after we find the minimum and maximum eccentricities at the end of the member or at transfer length, then we can do the same thing at midspan. So we can figure out our allowable tensile stress limit at midspan. We can also then figure out our bottom kern point at midspan. And here we figure out our minimum moment at midspan, our pre-stressing force after elastic shortening, and we can plug those values in to figure out our maximum allowable eccentricity at midspan. So our maximum allowable eccentricity here is 20.7 inches. So we can do the same thing at midspan with our minimum eccentricity, and you can see the values here, and we'll find a minimum eccentricity of 15.6 inches. So we now have an acceptable range of eccentricities at midspan. So we have our minimum eccentricity and our maximum eccentricity using our kern point analysis. So at midspan, if we keep our eccentricity between these two values, then we should meet our stress checks. So now that we have our ranges, we can actually select our locations for strands, or for our strands at the end and at midspan. Typically, you'll have a possible strand location grid for specific members. Strands are normally on a 2-inch by 2-inch grid. This allows for good stress distribution between the strands, and yeah, I guess the strand pattern has been checked for 1/2-inch and 6/10-inch diameter strands for most members. So looking at our available strand locations for our double T section, this is an assumed grid. I'm going to put all of our strands at midspan. I'm going to put them all towards the bottom of our section. So we're going to have 4 layers of 4 strands. So with the strand location, I can figure out the strand height at midspan just by looking at a weighted average. So I have 4 strands located at 1.5 inches. I have 4 strands located at 3.5 inches from the bottom, 4 strands at 5.5 inches from the bottom, and 4 strands at 7.5 inches from the bottom. And then I add those up, and then I divide by the total number of strands, so 16 strands. And that gives me the strand height at midspan of 4.5 inches. I can find the strand eccentricity from that then by taking the y from the bottom, 21.21 inches, minus this 4.5 inches, which will give us our strand eccentricity at midspan. We can do the same exercise here as the end of our members. So we are going to harp the strands. We're going to move all 4 rows of our strands up in our section, and we're going to move them so that our bottom layer of strands starts at 13.5 inches. So you can see here the location of my 4 rows of strands. Again, I'm going to do a weighted average. So my 4 strands at the 4 different heights divided by 16 total strands gives us a YP at the end of 16.5 inches. I can then find the strand eccentricity at the end by taking the distance from the bottom to the centroid of my double T section minus this 16.5 inches, which will give us a value of 4.71 inches. So you can see now our section that we're going to analyze. We have 16 half-inch diameter strands with a strand location at midspan shown here and a strand location at our end section shown here on the right. So this is going to be the section that we analyze moving forward to do our stress checks, our flexural strength checks, and our deflection checks. The first check that we're going to do is we're going to check the concrete stresses and make sure that they meet our prescribed stress limits in ACI 31819. As a designer, you're responsible that your beam meets the stress checks along the entire length of your beam, but we're only going to check it at 3 different points just to keep the example shorter. So we're going to check at transfer length, at 40% of the span length, and at midspan. So this 40% of the span length, when you have harped strands, your stresses may actually be critical at a point other than midspan or at the end of the section. So we're just picking 40% as a place between midspan and the transfer length that might be critical. We are going to need to check stresses at several different points during the beam's life. So we're going to check stresses at release and then also at service. And you can see our stress limits at release are dependent on if we're in the end of the beam or in the rest of the beam. So there are different stress limits in the end region of the beam. And then also at service, we need to check our compression under both sustained loads and the total load. So we're going to go through and check all these different stresses on the next couple slides. Before we check our stresses, we need to first calculate our actual pre-stress losses. When we were in the design process, we didn't know our section, we didn't know our strand area, we didn't know our strand location, so we had to assume some pre-stress losses to start. Now that we have our specific geometry and everything for our section, we can go back and calculate our actual pre-stress losses. So I'm going to use the PCI design handbook method. So this is a common method used for building design. If you're doing bridge design, you'd probably use AASHTO LRFD. But anyway, so the PCI design handbook method, we need to calculate our elastic shortening loss, and then we also calculate our creep, shrinkage, and relaxation losses. So first, with our elastic shortening loss, we need to calculate or find the jacking force, so the force in the strands at the time of jacking before elastic shortening. So we take our 202.5 times our total strand area to get that. We need our self-weight at midspan. So this is just the moment from self-weight at midspan. So we have our self-weight, WL squared over 8 to find our self-weight moment. We can then plug these values into our equation from the PCI handbook. So we have 0.9, which is for pre-tension members, times our P over A plus PE squared over I, and then take out our self-weight stresses. So that gives us the stress in the concrete at the centroid of the pre-stressing strands. With this stress, we divide by the concrete modulus to convert that into the strain, and then we take it times the pre-stress modulus to get that into stress in the pre-stressing. So we can find that our elastic shortening loss here, our actual elastic shortening loss is 13.6 KSI. Next, so this is our elastic shortening is a short-term loss. It happens immediately after the or immediately at the time of transfer. There are also 3 different types of long-term losses that happen. So we have creep, we have shrinkage, and we have strand relaxation. So we're going to calculate one loss term for each of these 3 components. Our creep loss, we need to find the moment from all of our superimposed dead loads. So that's our superimposed dead load, the distributed load, times L squared over 8, so WL squared over 8 for that, to get our superimposed dead load moment. We can use that to find the stress at the centroid of our prestressing strands caused by the superimposed dead load. And then the other factor that I show here is a KCR term, where our KCR is going to be equal to 2 for normal weight concrete. And essentially what this is a creep coefficient, so telling us how our concrete is going to creep over time. We can then plug all these values into the creep loss expression found in the PCI handbook. So you can see we're plugging those in. The only difference, or the thing to note here, is that EC is, so for elastic shortening, you use the modulus at time of release, ECI. Here for the creep loss, PCI tells you to use EC, so the modulus with your 28-8 concrete strength. So here that's 4,415 KSI. So plugging these in, we can find our creep loss to be 17.7 KSI. We can next find the shrinkage loss. So the shrinkage in concrete in our concrete member is going to be dependent on a couple of things. The 2 primary ones are the volume to surface area ratio. So how easy is it for the water to get out? How far does the water need to travel to get from the inside of a member to the environment? And then the relative humidity. So that's what pull is there from the external environment, pulling that water out from the member. So you can see here, larger volume to surface area ratio is going to decrease our shrinkage. So here our double T has a volume surface area ratio 1.79. You can see the units are inches when we're plugging it in, and we have a relative humidity of 70%. So when we plug in our 70%, we just plug in a 70 into the equation. So here we find a shrinkage strain, and then we take that strain times our modulus for our prestressing to get our total shrinkage loss. For relaxation, we need to use 2 tables from the PCI design handbook. So these are dependent on the type of the tendon and then also the amount of prestressing that's in the tendon initially. So for us, we're going to use grade 270 low relaxation strands. So we're going to be right here in our table. And we can use that to find our K relaxation and our J term. And then when we look at our C, our ratio of our initial prestress to ultimate is 0.75, so we're going to be right here. So our C term is going to be equal to 1. So we have a C of 1, and we have our K relaxation and our J defined by these tables. We can plug these constants into our relaxation loss equation along with our shrinkage, creep, and elastic shortening losses, and we can calculate our relaxation loss here of 3.5 KSI. Next, we can add all of our loss components together to get our total prestress loss. So we have our elastic shortening, our creep, our shrinkage, and our relaxation loss, and we add those together to get our total loss. With our losses, we can then calculate the stress and the force at time of transfer, and then also the stresses and forces at service. So at the time of transfer, we only take off the elastic shortening loss. So we have our stress in the strand before transfer, take off the elastic shortening loss, and then we have the stress in the strand after transfer. So take that times the strand area to get our total force in the prestressing strand after transfer happens. Service, when we're looking for the stress and force at service, we need to take off all the prestress losses. So we take off the total prestress loss component. So we can take that times our total area and we get our force at surface. So these are the forces that we're going to use in the stress checks on the following slides. So we're now ready to check our stresses. We're going to start by checking our stresses at release. So we're going to use force in the tendon approach, and we're going to use gross section properties. So you can see here some of the general top fiber and bottom fiber stress expressions. So we have our P over A component for our prestressing, the P, E, Y over I component, which takes into account the flexural stresses developed by the eccentricity of our strands. And then we have an MY over I component taking into account the flexural stresses from our externally applied moments or our moments. So here to, just to highlight, we're looking at release. So we're going to use our P sub I, our initial pre-stressing force that we found on the last slide. So this is the force immediately after transfer. So as an example, I calculate for us our top fiber stress at transfer, or at the transfer length. So you can see here how you calculate these values. So here, the top fiber stress at transfer we found to be negative 0.42 KSI. So my sign convention here is negative is compression. So compression is negative. So here we can see that this stress is, or the absolute value of the stress is less than the absolute value of our compression limit, so we're okay here. Then our bottom fiber stress, we can calculate to be negative 1.592, so 1.592 KSI in compression. And this is, the absolute value of this is less than our limit here, so we're okay here as well. You can see in this table the stresses at 0.4L and 0.5L as well. And in all cases, we meet our stress limits. So we're okay. All of our stresses check at release. We can do the same thing to find our stresses due to all the sustained loads. So when we're talking sustained loads, we're looking at kind of our final condition. So note that the force that we're using in these equations is the final pre-stressing force, the force in the pre-stressing strands after all losses happen. So that's a difference there. And then also we're looking due to sustained loads, so we include both the self-weight moment and also the superimposed dead load moment. So I'm including both those terms there. So you can see here as an example again, I'm finding the top and bottom fiber stresses at the location of the transfer length. So we can calculate the stress in the top fiber and stress in the bottom fiber and see that at the transfer length, the stresses check. So we're okay here and we're okay there. Looking at 40%, 50% length as well, our stresses are okay at these locations too. So we're okay here. We're okay with our pre-stress plus sustained load. The last stresses that we need to check are our service stresses, or our stresses from our total loads. So you can see here there's a final condition, so we're looking at we're using our final pre-stress force, and we include the stresses from our self-weight moment, the stresses from our superimposed dead load moment, and also the stresses from our live load moment. So you can see our stresses at this point are going to just be the stresses from our sustained load plus the stresses from our live load. So here as an example, I find the top and bottom fiber stress at 0.4L. So we have the stress from the previous slide plus the stress from our live load moment. And you can see here at 40% length, we have a compression stress of 1.29 KSI, which is okay, less than the absolute value being less than our limit. And then our tension stress is 0.483 KSI, which is less than our tensile stress limit. So I did this as well at the transfer length and at midspan, and we can see that all of our stresses are okay here. So our stresses at these 3 locations, check all of our ACI stress limits. Our next step is to check our flexural capacity. Again, we need to make sure that our flexural capacity checks along the whole length of the member. With harping or debonding, you may need to check more places than just midspan. So here we're going to check at 40% of the length and at midspan. At all locations, we need to make sure that our factored nominal moment is greater than or equal to our strength demand, so our MU. And we can also represent this as a safety index by taking phi mn divided by mu. We need to be greater than 1, but we want to be less than, about 1.3 or so. The higher this is, the less efficient our section is. For our section, we have harped strands, so we need to figure out the location of our strands along the length. So we're assuming that we have a linear profile along the length, so we can use this linear profile to determine our strand eccentricity at 40% length. We can use our eccentricity to figure out the depth of our strand. So we find the depth of our strand, or dp, by taking the eccentricity of our strand plus yt, the distance between the centroid of our section and the top of our section. So here you can see at 40% length, we have a D of 25.1. Next, we need to find our rectangular stress block coefficients. This coefficient is dependent on our concrete strength. Here we have 6 KSI concrete, so we'll have a beta 1 of 0.75. Next, we'll find the strand stress at ultimate, or our FPS. And to do this, we first need to find our prestressing ratio. So the prestressing ratio is just the area of our strands divided by B, the width of our compression block, or in this case, the width of the top flange, times dP, or 25.1 inches. So here you can see that we have a prestressing ratio of 0.001. Plugging these values into our FPS equation from ACI 31819, we can find our FPS to be 265 KSI. So this is the stress in the strand at the ultimate strength of the section. Using this, we can look at our equilibrium expression and set our tension force equal to our compression force. So we have our tension force from our strands equal to the compression force from our stress block, and solve for A, our unknown, which is the compression block depth. And we can find our A here to be 1.33 inches. Our neutral axis depth, or the distance from the top fiber to the point of zero strain, is going to just be A divided by beta 1, or in this case, 1.77 inches. We can then use this, our strain diagram, assuming a linear strain profile across the depth of the section, and we can figure out the strain at the centroid of our prestressing strands caused by this applied stress. So here you can see we'll find that strain to be 0.04. ACI defines a tension-controlled section as one in which this strain is greater than 0.005 for pre-stress members. So you can see that we are tension controlled, so we'll be able to use a phi of 0.9 moving forward. So we can then go back to our force and stress diagram, and we can sum our moments about the centroid of our compression block to determine our nominal moment. So we take our force component, APS times FPS, times our distance component, the distance between the centroid of our compression block to our steel. So that is 25.1 minus A over 2, 1.33 over 2, and we'll get our nominal moment, 15,864 kip inches. So we can then factor this by our 0.9 because we're tension controlled, and find our phi mn to be 14,278 kip inches. We can see here, dividing our phi mn by mu, we have a safety index of about 1.21. So we're stronger, but we're still kind of within a reasonable range. We can see we can do the same thing for our 0.5 length, so midspan. We can solve for phi mn and we can find a safety index of about 1.28. So you can see here we have sufficient flexural strength. So our beam checks our flexural capacity. We next need to check our reserve strength after cracking. ACI requires that our factored moment be at least 20% greater than the cracking moment. So we need to calculate our cracking moment. We can calculate the cracking moment by setting our stress in the bottom fiber equal to the tensile strength of our concrete, and then using force in the tendon to look at our different components. So we have our two prestressing, our axial stress from the prestressing, our flexural stress from the prestressing, and then our moment component from the applied moment. So kind of rearranging this, we can solve for M cracking, so the applied moment required to cause cracking in the section. You can see here I have a couple different terms. I'm going to use the section modulus instead of I over Y. So the section modulus is just our I divided by Y bottom in this case as SB. The rupture strength of the concrete, again, is 7.5 times the square root of F prime C. That's defined by ACI. And the pre-stress force at service, so when we're applying this cracking moment, is going to be PF, so 395 kips. We can solve for MCR and find a cracking moment here of 9,932 kip inches. So then we look at our limit and we can see that our phi mn is greater than 1.2 times our cracking moment. So our section has enough reserve strength after cracking. The last check that we're going to do in this example is we're going to check our deflections. We'll find our initial camber, we'll find our final camber, we'll find our deflections due to our sustained loads and also our live loads. And in the example, we're going to use all gross section properties, and we'll account for our long-term effects with our EC effective. For initial camber, we need to find our force after transfer, which we've done already. I'm just showing it again here. We're looking initial, so we're thinking short term, and we're also looking at initial, so we're looking at release. So when we find our EC, we want our ECI, so we're using our release strength of our concrete 4 KSI. So we can find our concrete modulus at release to be 3,605 KSI. Our deflection at initial camber is going to be a combination of our deflection from our pre-stressing and the deflection from our self-weight. So we can add these two components together to get our total deflection at release, and plugging in all of our different numbers, we can get our midspan deflection to be about an inch upward. So when we cut the strands, the beam's going to deflect upward due to the strand eccentricity, and it'll deflect upward about 1 inch at midspan. You can see here we take into account the harping of the strands by including the strand eccentricity at the end, or at the midspan, and the strand eccentricity at the ends here. So note that there aren't any specific initial camber or camber limitations at all. There are two reasons that we typically want to look at camber though. The first is that at the time of construction, we want camber to be relatively close between adjacent members. This allows easier connection between the members or easier placement of the deck on top. So that's one reason when that camber is important for us. You can take care of differential camber, but it's easier to take care of differential camber if you have a slab or a deck cast on top. So you can handle a little bit of differential camber if you have a cast in place slab or deck. The other reason that camber is important for us is it'll impact the functionality of the bridge or building. So one example here is bridges with excessive camber that aren't kind of smoothed out somehow can lead to kind of a roller coaster when you're driving over them. So those are two reasons why camber is important to us. Next, we're going to find our final camber. So with our final camber, we want to use our force at service and our concrete strength at service. So we can find both of those like we did before. We also need to somehow estimate our long-term effects. So we're going to do that here by using our creep coefficient, or a creep coefficient equal to 2. We could calculate the creep coefficient using any procedure that we wanted. We would probably use ACI 209R if we're designing a building, or AASHTO LRFD if we're doing a bridge. We're going to assume 2 here. And then we can use that to find our effective modulus. So just taking our modulus divided by 1 plus our creep coefficient will give us our effective modulus. We want to use our effective modulus for any sustained loads. So for us, the pre-stressing is sustained and the self-weight is sustained. So we're going to use our effective modulus for both of those loads. So here you can see the final camber. Including the pre-stressing and self-weight component is going to be 1.5 inches up. So over time, the beam is going to continue to deflect upward about 1/2 inch compared to the initial camber. We can next calculate our deflections due to our sustained loads and then also our live loads. So our superimposed dead load deflection. We're going to add that deflection here. The superimposed dead load is a sustained load, so we're going to use our effective modulus. And using our same equation, we can calculate our deflection from the superimposed dead load alone as 1.059 inches. We can add this to the deflection from our pre-stressing and self-weight to get our total deflection just from all of our sustained loads to be about 1/2 inch up. We can then calculate our deflections from our live load. Our live load is a short-term load. It's not sustained, so we're going to use just our regular concrete modulus EC. It's at service, so we'll find EC with our 28-day concrete strength. So you can see that value there. We have our live load, and we can calculate our midspan deflection from the live load alone as about 1 inch downward. Our ACI 318 limit, we're going to assume that the member is not attached to any structural elements that are likely to be damaged by large deflections. So this means that we need to limit our immediate deflection due to live load to less than L/360. So here we found about 1 inch deflection from our live load, and this is less than our L/360 of about 2 1/3 inches. We could also find our total deflection due to all the loading by taking our deflections from all of our sustained loads plus our deflection to live load, which would give us our total service deflection of about 0.6 inches down. So that concludes this example. Shown here is our final design for Flexure with the strand location at the midspan and strand location at the end of our member. You can see we're using 16 1/2 inch diameter strands, and we had a release strength of 4 KSI and an ultimate strength of 6 KSI. We checked the stresses, the tensile and compression stress limits in our concrete at release due to sustained loads and due to service loads. at 3 different locations. We checked, and all those stresses checked. We checked our flexural strength at 40% of the length and midspan. We checked our reserved capacity after cracking, and we also checked our deflections. We're going to learn how to design for shear later in this course, so I'm going to save that for a different example. But that concludes this video.